everybody. Today we will discuss about the error performance of the coherent QPSK modulation demodulation scheme. The demodulation scheme specifically is coherent, reminding us thereby that we are using a maximum likelihood receiver structure, that is the correlation receiver structure, where we have a correlation detector which utilizes the basis functions, and the basis functions in this case are the cos omega ct and sin omega ct terms with root 2e by t, is not it. So, those are the basis functions. So, it means that in the receiver we have to get the carrier references very precisely, and the corresponding demodulation scheme is QPA coherent. I am starting with a brief recapitulation which we have already encountered. This is an expression for the modulated signal SIT, okay. I may be 1, 2, 3, 4 as you remember, okay, and we will have 4 such signals for 4 symbols. Each symbol is made of 2 bits, information bits, and the corresponding received signal is always the added version of the signal with noise. So, R of t corresponding to SIT is SIT plus WT, capital WT, where WT is, what is WT, capital WT, we will say it is an additive white Gaussian noise process, okay. It is a continuous process, okay, and we will observe this over an interval 0 to capital T. Capital T happens to be the symbol interval, symbol duration, which is equal to twice TB, where TB is the information bit duration. This we have already discussed.
Sir,
yeah.
ESD of WT is assumed to be n0 by 2, or it has been calculated that it is n0?
No, we are assuming it to be n0 by 2. Okay. What we are assuming essentially is that it is something constant, because the noise we are calling as white noise. The noise power spectral density is flat over the entire bandwidth, okay. And how much is the bandwidth? We discussed earlier that theoretically the bandwidth is infinite, practically it stretches up to about 300 gigahertz or so, okay. So, we are talking about some frequency well within this bandwidth, and ultimately we know that our signal, modulated signal, is a narrow band pass signal, and hence we will ultimately what will matter for our demodulation performance is the in band noise, is not it. But in any case, the filtering we are assuming such that the noise power spectral density does not change really within that bandwidth, okay. So, it remains flat at the same level, okay. Now, this constant value we are assuming as n0 by 2, is that okay? You can call it as a by 2, okay. By 2 here indicates that we are talking about both sided power spectral density. If you visualize only the positive frequency domain, then the noise power spectral density single sided will be n0, is that okay? Okay. Now, do you recognize this diagram? I have redrawn, okay. So, what I have done is that I have shown the signal points, okay, and the corresponding energy is also indicated, and by these green dotted lines I have indicated the decision zones, is not it. There are 4 decision zones. This quadrant in this case is a zone, decision zone for the first symbol or signal, which is S1 bar, signal vector S1 bar. This is the decision zone for second signal S2, S2t, okay, or the corresponding signal vector S2 bar. Similarly, this is the decision zone for the third symbol, this is the decision zone for the fourth symbol, okay. Sorry, the decision zones are very regular for QPSK even. Now, the received vector at the output of the correlator bank, okay, at the output of the correlator bank will have 2 components for QPSK, is that okay? Okay, because we will have 2 correlators, okay, whose multiplicants will be phi 1 and phi 2, phi 1 t and phi 2 t, which are cos omega ct and sin omega ct term, okay. So, the correlator will have 2 output components, I am calling them as R1 and R2, okay, and R1 by our general definition is this integration of RT phi 1 t dt over 0 to symbol duration t, and you should calculate and find out that this expression comes out to be this root e cos 2 I minus 1 pi by 4 plus W1, okay. Tell me quickly if I have to understand at this point really, Okay. What is this term? I mean, is it a scalar or constant, or a low frequency term, or a high frequency term, or band pass signal or something like that? It is a scalar, isn't it? Because ultimately the correlator is integrating and I am sampling at the end of the integration duration. So, it is a scalar value. Similarly, R2 is this expression minus root E sin 2 I minus 1 pi by 4 plus W2. What are W1 and W2? Correlated version of noise, when noise is correlated with the basis function, okay, and is sampled, okay, and we have already discussed about this in the context of BPSK. There we had one component because there was only one basis function, and W1 was a random variable, Gaussian distributed random variable with 0 mean and variance the same as n naught by 2. So, here also we can say that W1 and W2, they are independent, identically distributed, which we sometimes refer as IID, Gaussian random variable with 0 mean and variance n naught by 2. So, here we will have two noise samples at the output of the correlator bank, okay, coupled with the corresponding signal components SI1 and SI2. Okay. And because R1 and R2, their R1 for example was W1 plus some fixed quantity and R2 similarly was W2 plus another fixed quantity, we can say that R1 and R2 are also sample values of an independent Gaussian random variable. That means, they are also Gaussian random variables, some values with mean of R1 is the mean of SI1, if you remember, and what is that? Root E cos 2I minus 1 pi by 4. Is that okay? And mean of R2 is root E sin 2I minus 1 pi by 4, the same as that of SI2. How I am saying this? Because we had a similar thing for BPSK also. Okay. So, this is an extension apparently, I mean very closely. So, I can say R1 and R2, they are random variables first of all. Okay. Randomness is because of the correlated value of the noise at the output of the correlator. Okay. That is how is the randomness, and the mean values are known. If I know the transmitted signal, I know the corresponding mean of R1, I know the corresponding mean of R2. Okay. And the variance is going to be dictated by the variance of the noise component W1 and W2. So, I can say R1 and R2, they are Gaussian distributed random variables, okay, with means root E cos 2I minus 1 pi by 4 and minus root E sin 2I minus 1 pi by 4, okay, and both of them have got the same variance of n naught by 2. Is it okay? Now, so, if you remember when we discussed about the output of a bank of correlators, our intention was to understand these RIs, RJs, so to say R1, R2, this received vector R, okay, statistically, and we saw that for additive white Gaussian noise channel AWGN, okay, these RJs, okay, they were independent Gaussian distributed random variables, okay, and we understood R1 and R2 in terms of the mean and variance of R1 and R2 or RJs in general. I said that, well, when I know that the random variable is a Gaussian random variable, complete knowledge is obtained once I know the mean and variance of that process. Okay. So, here also because of that same reason we found the mean, okay, and then we have also found the variance. Now, we are in a position to use our general rule of what is that likelihood function and finding out the probability of a particular event. This time for a change, okay, let us try to compute the probability of a correct decision. For BPSK, we consider the probability of a wrong decision. You can do it both ways really, there is no problem as such. Only thing is that if you, in some cases you will find that if you consider the probability of correct decision, your expressions may be simpler in between, okay, whereas if you pick up the probability of incorrect decision, the expression will unnecessarily be somewhat longer, though end result has to be the same in any case. Okay. So, here also I am considering the probability of correct decision. You can guess why, because we could see from this constellation diagram, there is a reason, of course, it is not very arbitrary, is that our decision zone, if I consider say S4 was transmitted, the decision zone is this quadrant. So, I am avoiding, if I would have tried finding the probability of a wrong decision, then I would have to consider 3 quadrants, okay, positive negative values of R1, positive negative values of R2. Instead of that, I am considering this zone. Say if I know that S40 was transmitted, then this is the correct decision zone really. So, I can see that both R1 and R2 are positive, or similarly for any other one, if I take the correct zone of decision, then I get fixed polarities of R1 and R2. That helps in avoiding some expressions, okay, but in general one can follow any approach. So, let us compute the probability of correct decision when a symbol is transmitted. Okay. So, let us consider that S40 is transmitted. S40 is in first quadrant, is not it? Okay. Can you guess anything about R1 and R2? Both are positive. Okay. So, we can say that from the signal space one can very easily see that this probability of a correct decision, I am using the symbol P of C when S40 is known to have been transmitted. That means, I am as if looking from the transmitter side, okay, and I have transmitted S40 and I am trying to guess what is the probability that this symbol is going to be received correctly. Okay. So, I am calling that probability as P of C, probability of correct decision when S40 is transmitted. Okay. What is this? From the signal space, I make use of the signal space, okay, and I can say it is a joint probability of the event, of the statistical event at the output of the correlator, that R1 is positive and R2 is positive, isn't it? This perhaps is the most critical stage in the derivation of the error rate expression for QPSK. Once you know that the probability of correct decision when the symbol is known, okay, is the joint probability of the event when both R1 and R2 are positive. In this case for S40, I can write an expression for PC S40, okay, because I know when S40 is known to have been transmitted, I know the mean of S40, a mean of R1 and mean of R2. What are the means in this case? Mean of R1 and mean of R2. If I tell you that S40 has been transmitted, under root e by 2, yes, it is root e cos 2I minus 1, okay, pi by 4, okay, and in this case it is 7 pi by 4. So, it is root e by 2. We can see that mean for both R1 and R2, they are also the same, is it not? Okay, though not for all the points really, but for this point S40, we now can say at this point that both mean and variance of R1 and R2, they are the same. Mean is root e by 2 and variance is, as we have stated, is n naught by 2. Okay. So, I can now find an expression for PCS40 is a joint probability, and they being independent, joint probability is the product of the two individual probabilities. Okay. So, you should tell me what is this expression. The first expression is the probability that R1 is greater than 0. The second one similarly is the probability that R2 is greater than 0. So, the joint probability is the product of these two probabilities. Okay. Now, I wish you do not look at this, okay, and try on your own and give me an expression for PCS40, a somewhat concise expression, and I will be happy if you can make use of your knowledge of error function or complementary error function in the process, because I can see that the expression structure is very similar to what we had encountered for BPSK. So, I guess some kind of ERFC, complementary error function, may appear really. So, try it out. You have got half a minute or 1 minute time. Is the question clear? The probability of correct decision when S40 has been transmitted from the modulator is this. uh, 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 is it expressed in terms of a complementary error function first of all? Okay, product of two, isn't it? Or is it that, see, yeah, you are on the correct track really. See, these two integrations have got the very similar structure. So if I change the variable here, okay, I get a similar structure basically. So I get some I square, whole square basically. If I is this portion, I get I whole square, is it not? The range is the same, okay. These are running variables, both of them can be substituted by x, isn't it? So what I can do is that I can put both r1 minus root e by 2 by n naught as z, okay, as well as r2 by root e by 2 by root over n naught as z really. So both the expressions have very same structure really, and I can say that this expression, probability of correct decision when s for t has been transmitted, is 1 upon root pi integration, okay, the limits will change, is minus root over e by 2 n naught to infinity exponential of minus z square dz whole square of this. Tell me if this is correct. Hmm? But you guys are not practicing too much, I find. Hmm? That will be necessary. We will set the question such that you have to do it. Okay. Now, and I should not have showed you this, that okay, from this expressions, whenever you have got integration of a to infinity e to the power minus z square dz, you have to recollect that okay, there is a complementary error function associated here, we can express it better to that really. So here this expression can be put in terms of complementary error function, okay, just to remind you that 1 upon root pi integration of minus a to infinity e to the power minus x square dx with little bit of manipulation can be expressed as 1 minus half ERFC of a, okay. So making use of that, we get a somewhat compact expression, I should say, of PCS4T. The expression is 1 minus half ERFC root over e by 2 n naught whole square. And tell me quickly, what are the symbols involved in this e and n naught? N naught is a single sided power spectral density in watt per hertz, and e is the capital E in this energy per symbol, isn't it? In fact, this probability is the probability of an correct decision of a symbol S4, isn't it? Now I expand it, fine, and can make some observation even really. So this is the probability of correct decision sorry, when S4T has been transmitted. I can now very easily get the corresponding probability for wrong decision or erroneous decision, okay. So I am expressing it as P of E, PE, probability of erroneous decision about the symbol when I know that S4T has been transmitted. So PE S4T is 1 minus PC S4T, because I know S4T has been transmitted. So either I make a correct decision or a wrong decision. So this was the probability for correct decision. So the probability of wrong decision is 1 minus this probability of correct decision, and the expression is shorter. It has got two terms now. Ultimately, we are interested in the probability of error, I mean erroneous decisions, isn't it? Error performance we are more interested in. So probability of error, when I know S4T has been transmitted, the probability of a wrong decision about that symbol only is ERFC root over e by 2 n naught minus 1/4 ERFC square root over e by 2 n naught. Okay. Now this is the probability of error when I knew the symbol, a particular symbol was transmitted. Is it not? Okay. So can you tell me what would be the probability of error expression for S1T, PE S1T? Same. Okay. PE S2T, same. Okay. So we can see that once I get an expression for error for a particular signal symbol S4T, I get the expression for the other symbol errors as well. Okay. Then I can even talk about an average symbol error rate, isn't it? For that, what do I have to know? the probability of occurrence of the symbols at the input to the modulator, is it not? For BPSK, what did we assume? We assume that each bit was equally likely. For QPSK also, we assume that, sorry, that all the symbols are equally likely, and hence you can say that the average probability of a symbol error, I need not talk about S40, I need not mention about S40 or S1T, etc. I can say the average probability, averaging is very easy because all the symbols are equally likely. If they were not, somebody had a question, we did discuss something on that really. If you find that for a situation these input symbols are not equally likely, so try to assess the probability of the symbols. Symbols are always finite in number, that is how symbols have been constructed, n m capital M number of symbols. So try to find the probability distribution for all these symbols really, make use of that here in this step really, and this will not be so simple, but it is straightforward in any case really. So when the symbols are equally likely, the probability of occurrence of each symbol is 1 upon 4. Okay, I can find an average probability of a symbol error. Okay, and I am calling that, I am noting that by this notation P of E, PE. We had a similar expression for similar notation for BPSK. So by PE, we will indicate the probability of symbol error.
So even if the probabilities are not equal, even in that case also the probability of error will be, I mean, same as the average probability of error, it will be same as probability of one symbol.
Not necessarily.
So the distribution of the symbols will be equal.
See, here the average probability of a symbol error means you have generated the symbol, okay, with some probability distribution, and then you are finding out the average probability of symbol error. Okay, that is the expression we are finding out. Okay, what you mean to say is that the sum of the probability of the symbols at the input to the modulator is always 1. That's well taken. That's well taken. That's well taken really. Okay, but what if they are different really? You had to put the different values, and you had to find out if the modulation, that's in general really, if the constellation is not so uniform. If in that case you had to consider the input probability distribution, and the, if this expression was not the same for all symbols really. So you have to consider the respective symbols with the respective.
All the symbols are not equally likely. So this will only change by a constant.
In this case, it would not change. See, his question understood. His question is, if the symbols are not equally likely, then would there be any change in this expression for PE? This expression would remain the same. Okay, this expression also for any SI, it would remain the same, isn't it? That means this portion would remain the same. Okay, then would this overall expression PE change? Which constant? Which constant? It won't change. It won't change. But again, let me remind you that is specific to this modulation scheme QPSK, where for any SIT we had similar expression for symbol error. Okay, but we had encountered some QAM kind of modulation scheme. If you remember, the error expression from the signal space itself one can guess is not going to be the same for all symbols. Okay, so for those modulation schemes, this portion would not be the same. Okay, and hence with the respective probabilities, the corresponding symbol error would get weighted, and the end expression would be more elaborate.
Sir, can we extrapolate that for all modulation schemes which have the same distinct boundaries? The identical the same boundaries, the error PE will be same for all the things.
Yes, because this is the average probability of it. Okay. Yeah.
If all signals are not equally likely, then the average bit error rate will be
Different.
It will be.
Okay. Now we make some simplification. We have got an expression for PE, okay, which is still in the form of ERFC root over E by 2 n naught minus 1 by 4 ERFC root over 2 by E by 2 n naught whole square of the second term really. Okay. I mean, I asked you to find out. In fact, we did tabulate some values of ERF or ERFC. Okay. So guess out of these two terms, which one is going to be more important really? ERFC. Okay, especially when this argument is somewhat large. Okay, the first term is going to be much more dominating compared to the second term. Okay, and a larger argument means what? if this E by 2 n naught, that means if my E by n naught for the system is considerably is good enough, isn't it? What kind of situation does it mean? Can you visualize? Low noise, that's right, low noise and hence low error. Well, he says high signal power. I will say, well, signal power should always be the minimum which is necessary. That way, yes, okay. But otherwise, I would not buy your idea of increasing signal power that way. We have discussed that, right? Okay. So, yes, the point is that if this when the argument is large, we can make some approximation. It's obvious here, okay. And that means when E by n naught is considerable, which means the situation is not very bad, noise is not influencing the signal not too much really, and hence the corresponding error rate is also very small, which means I can now say mathematically, if I am interested in finding the asymptotic value, okay, for moderate or high SNR condition, then gradually this is going to be vanishing really, okay, and we can go for approximation. But if you do not like to go for approximation, if you want to remember this part, it's well and good really, okay. And we can see that when the signal to noise ratio is not very good, okay, then there is going to be appreciable difference between the approximation that we are going to make and the actual error rate really, isn't it? This term is going to be more and more prominent, okay. Now, which way it is going to be prominent really? I mean, this argument is always positive, okay. So, is it that if I approximate, the approximation, obvious approximation is that we try to neglect the second term. In that case, only the first term survives, okay. But suppose I remember only this part and my signal to noise ratio is not very good really, E by n naught is not very high. In that case, am I going to overestimate or underestimate the error performance? Yeah. And because we are overestimating, it is not again a very bad idea, because the designer, okay, I mean he gets a value which is somewhat more than what it will actually be in practice, isn't it? So, if he uses this expression in his design, I mean he is sort of overprotecting his system, okay. Anyway, so there are enough justifications for some kind of approximation, starting with that simplification of this expression, so that we remember easily, which is more important for us. Well, so we note that for moderate as well as large, it is better, the approximation is better if SNR is higher. E by 2 n naught is greater than 1. This is a thumb value, approximate value really. If it is close to 1 or even greater than 1, it is good. We can say that probability or the average symbol error rate, let me go on giving some different names so that you do not get confused really. Average symbol error rate or simply symbol error rate, average is implied. Whenever we talk about rate, we mean an average, appropriate averaging. So, the symbol error rate PE is approximately ERFC root over E by 2 n naught. Easy to remember, okay. So, the symbol error rate expression for QPSK is ERFC root over 2 E by n naught, root over E by 2 n naught, sorry. And this one may like to rearrange in this form. E is the symbol energy, so one can map it to an equivalent energy per information bit, because 2 bits made 1 symbol, okay. So, one may also like to express this expression as ERFC root over EB by n naught. Is it not? Where E is the symbol energy, energy per symbol, which is twice EB, where EB is E by 2, half of the symbol energy, which I can say is the energy per information bit as if has been transmitted, okay. Okay, precisely it should be the received energy per information bit, because it is in the receiver where this ratio is going to matter. So, to be correct really, EB is the received energy per information bit, okay. So, the average symbol error rate for QPSK in AWGN, additive white Gaussian noise channel, is PE is approximately ERFC root over EB by n naught, okay. well, is his question understood? His question is whether a value of n naught, does it depend on the circuit? Yes, it will. Yes, no, it will not. Well, where from this n naught comes? Channel, but I don't like you to say only channel, because you have talked about various kinds of channel. Which channel you are talking about? Is it propagation channel or radio channel or modulation channel? To be on a safer side, yes, modulation channel, because that's the one channel in between the modulator and the demodulator. Okay, correct answer. Okay, but is this n naught predominantly available in the propagation channel? We have discussed this point. Yes, he is correct. It's usually not in the propagation channel. Where is it then? Actually, now if I try to find the answer, yes, as he said, as he raised his doubt nicely, that this is the noise in the low noise amplifier in the receiver circuit. That's what is the thermal noise. That's what is usually modeled as additive white Gaussian noise. Okay.
If we trace the source of the noise in the LNA, so eventually it's a noise of the channel that's coming into the LNA. I mean,
Slowly, slowly, if you try to trace the source of noise in the LNA, right?
eventually coming from the physical channel itself.
No, no. The noise component usually from very say fixed point to point wireless channels, okay, is not much from the propagation channel. Most of the noise is generated within the low noise amplifier.
I mean, like,
How?
the low noise amplifier generate noise. I mean,
Why should the low noise amplifier generate noise? Any suggestion? Thermal effects. Thermal effects in which components? He is asking about the low noise resistance only. All passive as well as active components. Okay, the passive components also will have some leakage value really, isn't like capacitance. Inductor will have a small resistance. So whenever, if you have a component which dissipates energy, okay, dissipates power, like resistors, like your active devices, transistors, okay, and even some leaky resistance, fine, you generate, I mean, some thermal noise is generated over there. So the actual noise is generated in a distributed manner in the LNA, irrespective of the design. The amount is different, okay, but it is generated in all the components which dissipate some power really. And so if you are trying to specialize in LNA design, you have to map the distributed noise sources. This is not necessary for us. So what we are considering is an equivalent lumped noise, okay, and then an ideal LNA. So just yeah.
element itself, the resistors or the capacitors, they are present even in the other components. Like a filter.
Yeah, that's the other
So
question.
why would you say that only the LNA is going to
Yes, that's a valid question. So let me not. Yeah, his question is his question understood? His question is, why is it that we are talking about LNA only? Why not other components? Yes, that's the reason. That's the reason. Okay. So because the signal itself is very weak and your amplifier has to amplify that small signal. Have you ever designed, you have designed some CE amplifier, okay, you found some signal handling capacity. There you are interested in finding the maximum signal energy that will be signal amplitude that will be amplified without distortion. Did you bother too much to see what is the minimum signal amplitude? You said, well, it was amplifying 10 millivolt, 5 millivolt signal. But what happens if the signal amplitude is even smaller? If it is in the range of microvolt, the common transistor that you may have used will not at all give you an amplified output really. You will find the output with a lot of scale adjustment on the CRO as somewhat noisy. Very difficult to see, very difficult to synchronize the CRO, okay, even if a sinusoid is being amplified there in the amplifier, okay. So when the signal amplitude is really low, okay, this device, amplifying device, comes into picture really. It doesn't work ideally from 0 voltage really. I mean 0.1 nanovolt or something like that. It doesn't work, okay. So analysis and modeling of transistors, they are done for different ranges of signal, which is of interest really, okay. So small signal analysis, smaller than what you have analyzed incidentally, is a different game altogether, okay. So now coming back to our modeling really. So because LNA faces the first signal really, which tries to amplify this. So the signal which reaches the LNA, okay, may have some noise, because of the other RF portions in between beforehand, really, like the antenna matching unit, etc. Okay, still those are smaller usually for good design, a good choice of those components really, and the LNA generates noise, thermal noise from dissipative components, all dissipative components. We take them out. We say that as if here is a noise, equivalent noise due to LNA, and this LNA is an ideal LNA. So, to find an expression for the output of this signal, what we do is that we consider what actually goes into this ideal LNA, which we say is a signal plus noise, and that has a gain, nominal gain of 10 dB, 12 dB, and you get the output expression. Okay. So, all the noise which may have occurred, say in the antenna, in the matching unit, as well as in the LNA, they are clubbed together. Okay. Now, this we have not talked about a cascaded receiver structure. It can be shown there really that when you go down the chain, really the subsequent devices, you may have a mixer or frequency converter, down converter, you may have some IF amplifier stages, etc. As you go deeper and deeper, okay, the effect of each of these blocks generates noise, okay, but the overall effect of their noise is much less compared to the effect of noise generated in the very first stage of the LNA and the front end of it in the antenna, etc. That can be shown, but we did not show that really, because the total receiver noise and noise modeling we did not try. So, primarily it is the LNA noise which we are modeling. Okay. There may be similar kind of noise from other passive devices like antennas, etc., and some contribution from the downstream blocks, signal processing blocks as well. Okay. Well, now ultimately, if we are feeding a serial bit stream to the modulator, we would be interested in a bit error rate expression as well. Okay. Guess what is the bit error rate expression for QPSK? We have got an expression for the symbol error rate. Note that is equal to symbol error rate. Well, why? Justify. All right. Yeah, it's less probable. But the point is that now when you so what he is trying to say is that the signal points are well chosen through gray coding, okay, which we had included in our example. Okay. So, one symbol error usually means one bit error, is it not? One symbol error means one bit error, but the point is that one symbol carries 2 bits. So, if I say my error rate is 10 to the power minus 3 and I have transmitted 1000 symbols, okay, can you tell me how many symbols were received erroneously? One symbol, is it not? So, my error rate is 10 to the power minus 3, we have transmitted 1000 symbols. So, number of erroneous symbols at the output of the demodulator is 1. So, one symbol was received in error, and then by gray coding we can guess that one bit is in error. So, out of 1000 symbols we have one bit in error, but in 1000 symbols how many bits we have transmitted? 2000. So, what is the bit error rate? 1 by 2000, not 1 by 1000. So, what is the bit error rate? Symbol error rate was 10 to the power minus 3, bit error rate is half into 10 to the power minus 3, which is 5 into 10 to the power minus 4. So, bit error rate approximately is half of symbol error rate, is it not? Okay. So, that is what. No, not really, but we can say that unless the E by N naught is very small, I mean very small, those events are much less likely compared to the other kinds of events where single symbol error means single bit error. See, we have already made some approximation in our expression for symbol error rate. Okay. So, that is incorporated in that. In fact, these events that you get 180-degree phase shift and then an error, okay, is much less likely when the signal to noise ratio is moderate or high. For low signal to noise ratio, you may have such cases, and you have to look for more precise expression. I will read out. So, I am now trying to get an approximate expression for the BER. So, average bit error rate by definition should be, if I am observing and then trying to find an expression, is the ratio of the number of erroneous bits received divided by the total number of bits transmitted, which have been received, which have been transmitted, where this total number of bits I am indicating as n tot TOT, and this n tot should be as large as possible. I must be patient enough to receive and observe a good number of, very large number of such received bits really. So, I am saying limit n total tending to infinity. So, this is an acceptable definition for the bit error rate. Okay. So, as we discussed that assuming gray coding, you may write that the number of erroneous bits is equal to number of erroneous symbols. Okay. This is actually correct or close to the actual scenario when the SNR is moderate or high. Okay. To remind you, I have noted here, and then the total number of bits received is twice the number of symbols received. So, this expression, if I now express in terms of symbols, I ultimately get the average bit error rate is half limit of number of erroneous symbols received divided by the total number of symbols received. Total number of symbol I am calling as NS, which is half the total number of bits transmitted. So, here I am saying NS tending to infinity, and this expression is half of PE, which is half ERFC root over EB by N naught. My symbol error rate was ERFC root over EB by N naught. My bit error rate approximately is half ERFC root over EB by N naught, and we recognize that this approximate expression is identical to the bit error rate expression for BPSK. Then you tell me, why should I not choose QPSK, okay, over BPSK? Why should I not choose QPSK? Well, when you need simpler circuit, you choose QPSK or you choose BPSK. Okay, right. Well, yeah. Pardon? No. See, this expression is same as that of BPSK. Okay. So now what matters is this argument EB by N naught. Let me put a bracket here. So I have missed this bracket. Okay. Yeah. So my point is that for the same EB by N naught ratio, EB in BPSK also is the energy received per information bit. EB in QPSK here is the same, is the energy received per information bit. N naught, if I consider the same propagation channel, same modulation channel, is the same for both the cases. Okay. So under this condition, my question was, why should I choose BPSK and not QPSK? His suggestion, rightly so, has been that only when I have to have a very simple demodulator structure. Makes sense, okay? But otherwise, I am finding a stronger point for QPSK. Once, but bandwidth, okay, bandwidth is half as that of BPSK, because we said approximately QPSK means two independent BPSK streams are going. Okay, so the symbol rate is half as that of bit rate. So QPSK needs half the BPSK bandwidth, and now I am finding both BPSK and QPSK has very similar bit error rate, identical bit error rate for high signal to noise ratio. Okay, so if I know my channel condition is not going to be very poor, okay, then I should choose QPSK, unless I mean I have to design a very simple kind of receiver structure. Okay, so QPSK is a strong favorite because of these two fundamental issues. It needs smaller bandwidth, it ensures almost the same performance as that of BPSK. Okay, yeah, right. We are talking about the no, we are talking about the receiver. The LNA is in the receiver, so there is no power amplifier after the LNA. The signal was very weak. The signal has been amplified to some extent. Say it has been amplified by 10 times. The next stage usually is down converter, the mixer. Okay, the mixer, a passive mixer has gotten loss. Okay, some active circuitry, transistor based one are available, many are available really, which I mean avoids this loss too much really, but still on the whole you have some loss there. The main amplification comes in the after down conversion in the IF stage. Well, his question is till how much amplitude the LNA amplifies that till. You mean the how much maximum amplitude? Well, you have read about AGC in earlier course, automatic gain control. Okay, the AGC normally applies on the IF stage, but sometimes it also applies on the RF stage to check, to limit the maximum amplitude of the signal which may go into the LNA, because you may have a situation where your receiver may be very close to the transmitting antenna, and instead of a very weak signal, a very strong signal can come into the LNA, and which may again drive the LNA in the nonlinear region, or even may drive even may damage your LNA really. So to protect such issues, some AGC is covered there if such situations are envisaged really. In any case, the typical amplitude of the LNA output, let me say, is of the order of still of the order of a few tens of microvolts or hundreds of microvolts, still very low. Okay, just sufficient so that the next stage of mixer, active or passive, operates properly. Okay, well, quickly before we stop here, this diagram is very important. It's very important. Okay, and here we have plotted those mathematical expressions. We are plotting the symbol error rate in general versus EB by N naught expressed in dB. Okay, we have two curves because we have discussed about the error performance of two modulation schemes, BPSK and QPSK. Can you quickly tell me what is this dark curve for? It's for BPSK or QPSK? Pardon? I am plotting symbol error rate. BPSK. This curve gives a better presents a better picture, or this curve presents a better picture. If I do not tell you about the modulation schemes, which modulation scheme would you choose from these two curves? Lower one. Why? Because for the same or for a particular EB by N naught, I get lower bit error rate for this modulation scheme. So I will choose this one. Okay, fine. So tomorrow if I draw a curve on the right hand side, on this side, okay, the performance is going to be poorer compared to BPSK, isn't it? So an overall emphasis is to get modulation scheme, okay, I mean so that the curve is closer to the left hand side as much as possible, and BPSK there is a benchmark, okay, for so far as symbol error rate is concerned. I plotted the symbol error rate for QPSK by this green line. How is it looking? The symbol error rate curve is not identical to bit error rate curve. It should not be, because the expressions are different. In the first case, for BPSK we have half ERFC root over EB by N naught. For QPSK we have got ERFC root over EB by N naught. Okay, fine. Approximately in this portion, when EB by N naught is high, this expression does not apply in this region. You should remember that. Okay, I have plotted this expression here, but the actual symbol error rate curve in this region will not be following this curve just now discussed. Okay, so this is the symbol error rate curve. Now if I ask you to draw the bit error rate curve for QPSK, I can quickly sketch. How is it going to be? It's going to be very same. Sorry, well, it is going to be same as BPSK. There will be some deviation here perhaps when the EB by N naught is smaller. Okay, fine. A few values you should remember. You should remember that BPSK or QPSK bit error rate. Okay, bit error rate for BPSK or QPSK is 10 to the power minus 5 when EB by N naught is 9.6 dB. Okay, if the EB by N naught is 9.6 dB, the bit error rate for BPSK or QPSK is 10 to the power minus 5. To get a bit error rate of 10 to the power minus 4, you need a bit error rate of, you need an EB by N naught of 8.4 dB. To need a bit error rate of 10 to the power minus 3, the corresponding value of EB by N naught is close to 6.8 dB. So remember these 2-3 values, because these values will come over and over again when you read digital communications later. Is that okay?
10 to the power minus
6.8. Okay. So this blue curve is the approximate BER for QPSK. Is that okay? Any question? Okay. Thank you very much. That's what we explained. That's what we found. That between BER curve and ACR curve, see, there will be a half term really, isn't it? In the symbol error curve, it was only ERFC root over EB by N naught. In the bit error rate curve, there will be a half, because each symbol carries 2 bits, and one symbol error means one bit error.